The topic today is law of conservation of mass and balancing of chemical equation. Let's do a little review of what we did in the last video. We have reactants and products, and we know what subscript is. You see subscript? Coefficient is. And here, we want to look at the hydrogen and oxygen in the reactant side, the hydrogen and oxygen on the product side. In other words, we want to count the atoms, which we did already. So for hydrogen, there are 2 sets of hydrogen, which gives us a total of 4 hydrogen on the reactant side. And there's 2 atoms of oxygen on the reactant side. Then on the product side, there are 4 atoms of hydrogen and 2 atoms of oxygen. So we have the same amount of each kind of atom is equal on both sides. Each kind of atom is equal on both sides. Okay? Then let's continue. So now we want to count. Yeah, we can do this, but let's count again. How many oxygen atoms on this side, on the reactant side and on the product side? Okay, so we have, but this, let me correct something. Okay, I think this is easier to understand. So here, given this equation, we have the reactants, reaction takes place here, we have the products. Now, we have CH2, methane, oxygen, 2 sets. That's why we have the coefficient 2. 1 set of CO2, and then 2 sets of water. Now, if we count the number of each kind of atom on the reactant side and the product side, let's see. There's 1 carbon on this side, 1 carbon. There's also 1 carbon on this side. I want you to count the hydrogen on the reactant side and hydrogen on the product side. Also count the number of oxygen on the reactant side and oxygen on the product side. I want you to pause the video and count it. Okay, hopefully you find out that there's 4 hydrogen atoms on this side, 1, 2, 3, 4 hydrogen atoms on this side, and there's 1, 2, 3, 4 oxygen on the reactant side, 1, 2, 3, 4 oxygen on the product side. So if each kind of atom is equal on the reactant side and on the product side, that means this follows the law of, agrees with law of conservation of mass. Conservation of mass. That means the mass of the reactant is equal to mass of the product. Look at it. We haven't done how to calculate, but assume, just take only what we see here. The mass of CH2 is 16 grams here. The mass of O2, which is the mass of all of this, the mass is 2 times 32, right? You add this together, it becomes 80 grams. Then you do the same thing here. The mass of CO2 is 44 grams. The mass of 2 sets of water is 2 times this. Then you end up with 80 grams. Of course, if each kind of atom is the same on reactant side and product side, the mass will also be the same. And when this happens, we say that this follows the law of conservation of mass. Okay? So this is the reaction. So anytime you start a reaction, the reaction of your reactants, the mass of your reactants will be equal to the mass of the products. That's what that means. So we can also count each kind of reactant, each kind of atom on the reactant side and each kind on the product side. Look at the reactants here. Carbon, you count, this is carbon, this is carbon, this is carbon, but remember there's 2 here. If you do it correct, you get 5. Then this is carbon here, this is carbon. Okay, if you do it correctly, add it up, it will give you this. Remember, coefficient means there are 2 sets of this, in case you forgot. Hydrogen, there's hydrogen here, there's hydrogen here. Okay, on the reactant side, there's hydrogen here, there's hydrogen here. Then you got this. Then oxygen, you have oxygen here, you have oxygen here, then you have oxygen here, you have oxygen here, you have oxygen. So oxygen is 7 on each side. Then sodium, there's sodium here, and then there's sodium here. So you find out that each kind of atom is equal on the reactant side and the product side. Okay. What does that mean? Let's look at more examples. You are given a reaction. You say in a reaction, 5.3 grams of sodium carbonate. Sodium carbonate is this. Okay. Reacted with 6 grams of acetic acid. Acetic acid is this. Okay. The products were 2.2 grams of carbon dioxide, which is this, 0.9 grams of water, which is this, and 8.2 grams of sodium acetate. Now, we want to check how much of the reactants and how much of the product. Then mass of sodium carbonate is 5.3, mass of acetic acid, this should be, so this is mass of acetic acid as shown here. Okay. Okay, here, so acetic acid is 6 grams. If we add total of all the reactants, the mass of every substance on the reactant side, it gives 11.3. And then on the product side, we have carbon dioxide 2.2, mass of water 0.9, sodium acetate 8.2. We add it is also 3.3. So the total mass before reaction equal to the total mass of product. Okay. Remember, we counted the atoms here. We counted the atoms here. Each kind of atom is the same on both sides. So when this happens, we say that it agrees with law of conservation of matter. Or sometimes they say law of conservation of mass, which means matter cannot be created or destroyed, only change from one form to another. Matter cannot be created or destroyed, but can only be changed from one form to the other. Let's look at this again. If you are looking at this, we have carbon on this side, we have hydrogen, we have oxygen. We didn't end up with nitrogen here. If we did, we've destroyed matter and we've created matter. So for every reaction that happens, it will end up with the same kind of atoms and the same amount. Okay? That's why we call it law of conservation of mass, because the mass of the reactant must be equal to the mass of the product. If not, it's not following, it's not agreeing with law of conservation of mass. And if each kind of atom, like here, let's say this is 5, this is 4, they are not equal, each of them is not equal, is not following, is not agreeing with law of conservation of mass. So it must, that's why this because the total mass before reaction equals the total mass of product, this follows the law of conservation of mass. So this is correct. This video will help in understand this better,
Where does all this stuff come from? This rock, that cow, your heart. Not the things themselves, mind you, but what they're made of, the atoms that are the fabric of all things. To answer that question, we look to the law of conservation of mass. This law says, take an isolated system, defined by a boundary that matter and energy cannot cross. Inside this system, mass, aka matter and energy, can neither be created nor destroyed. The universe, to the best of our knowledge, is an isolated system. But before we get to that, let's look at a much smaller and simpler one. Here we have 6 carbon atoms, 12 hydrogen atoms, and 18 oxygen atoms. With a little energy, our molecules can really get moving. These atoms can bond together to form familiar molecules. Here's water, and here's carbon dioxide. We can't create or destroy mass. We're stuck with what we've got. So what can we do? They have a mind of their own. Let's see. They've formed more carbon dioxide and water, 6 of each. Add a little energy, and we can get them to reshuffle themselves to a simple sugar and some oxygen gas. Our atoms are all accounted for, 6 carbon, 12 hydrogen, and 18 oxygen. The energy we applied is now stored in the bonds between atoms. We can re-release that energy by breaking that sugar back into water and carbon dioxide, and still, same atoms. Let's put a few of our atoms aside and try something a little more explosive. This here is methane, most commonly associated with cow flatulence, but also used for rocket fuel. If we add some oxygen and a little bit of energy, like you might get from a lit match, it combusts into carbon dioxide, water, and even more energy. Notice, our methane started with 4 hydrogen, and at the end, we still have 4 hydrogen, captured in 2 water molecules. For a grand finale, here's propane, another combustible gas. We add oxygen, light it up, and boom, more water and carbon dioxide. This time we get 3 CO2s because the propane molecule started with 3 carbon atoms, and they have nowhere else to go. There are many other reactions we can model with this small set of atoms, and the law of conservation of mass always holds true. Whatever matter and energy go into a chemical reaction are present and accounted for when it's complete. So if mass can't be created or destroyed, where did these atoms come from in the first place? Let's turn back the clock and see. Further, 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 too far. Okay, there it is. The Big Bang. Our hydrogen formed from a high-energy soup of particles in the 3 minutes that followed the birth of our universe. Eventually, clusters of atoms accumulated and formed stars. Within these stars, nuclear reactions fused light elements such as hydrogen and helium to form heavier elements such as carbon and oxygen. At first glance, these reactions may look like they're breaking the law because they release an astounding amount of energy seemingly out of nowhere. However, thanks to Einstein's famous equation, we know that energy is equivalent to mass. It turns out that the total mass of the starting atoms is very slightly more than the mass of the products, and that loss of mass perfectly corresponds to the gain in energy, which radiates out from the star as light, heat, and energetic particles. Eventually, this star went supernova and scattered its elements across space. Long story short, they found each other and atoms from other supernovas, formed the Earth, and 4.6 billion years later, got scooped up to play their parts in our little isolated system. But they're not nearly as interesting as the atoms that came together to form you, or that cow, or this rock. And that is why, as Carl Sagan famously told us, we are all made of star stuff.
From what we now know so far, pause this video. Does the equation below agree with the law of conservation of mass? Remember, law of conservation of mass says that Matter cannot be created or destroyed, but can only change from one form to the other. Okay? Cannot be created or destroyed. So, what do you think about this? Pause the video. Hopefully, since I did not give you the mass of each of the substances, hopefully you counted the number of atoms on the reactant side and the product side. So let's start by counting the chlorine. Chlorine is the green one, 1, 2, chlorine, there's 2 here. And over here, there's 2 because coefficient here is 2. So they're equal on both sides. Let's count calcium. There's 1 calcium here. There's 1 calcium on the product side that agrees. Let's count carbon. There are 2 carbons here. There are 2 carbons here because this carbon, there's 2. You remember? This means there are 2 sets. And there are 2 carbons. Sorry. This carbon here. You see this? There's another carbon here. So there's 2 on both sides. Then there are 1, 2, 3, 4, 5, 6 hydrogen atoms. No. Oxygen. I'm sorry. Oxygen atoms. 1, 2, 3, 4, 5, 6. Oxygen there. You see, this is 3. There's 2 sets, therefore 6. And then over here, 1, 2, 3, 4, 5, 6. So each kind of atom is equal on both sides. Therefore, it does agree with the law of conservation of mass. If each atom is equal on both sides, that means the mass will be the same because the mass of each atom will be the same. So if you add it up, the mass will be equal on both sides also. Let's look at this one. The same way we count, let's do this one together. 1, 2, 3, 4, 5 oxygen. 1, 2, 3, 4, 5 oxygen. There's 2 carbon here. 3. There's 2 carbon here. 3 is not very clear, but from the chemical equation, you can get from the formula, you can get that. Then hydrogen, 1, 2, 3, 4. 1. So hydrogen is 4, 5. Okay. So something is hiding. 4, 5, right? There's 1 here, 1 here. There's 4 here. So from the equation, we know there's something hiding behind here. So it's 5. Then 1, 2, 3, 4, 5. You see, equal on both sides. Then have we counted the oxygen? Yes. So they are equal on both sides. Therefore, it does agree with law of conservation of mass. Then this one is easier than the last one. We do the same counting as long as each atom is okay. Here we start with pink. This is 1. This is 2. We don't even have to continue. Okay, this is hydrogen 1 here. There's 2 here. Wow. So then there's 1 here, there's 1 here. This one does not agree because each kind of atom is not equal on both sides. So this one does not follow the law of, agree with the law of conservation of mass. For each two, because what this means is that matter is destroyed or created. Okay, how can we have 1 here and have 2 here? Okay, we must end up with what we started off with. Whatever amount we started off with, we have to end up with that, but that's not what is happening here. So this one does not agree with the law of conservation of mass. So when we have this, because it doesn't agree with the law of conservation of mass, we have to balance the equation. the significance of balancing the chemical equation is for the chemical equation to agree with the law of conservation of mass. So for every chemical equation we have, it must be balanced. If it's not balanced, then matter is created or destroyed. That means it doesn't agree with the law of conservation of mass. So we will balance chemical equation, okay? Again, the significance of balancing chemical equation is that every reaction must follow, agree with the law of conservation of mass. Whatever you started off with, whatever amount you started off with, you have to end up with the same amount. Whatever kind of atom you started off with, you have to end up with the same amount on the reactant side and the product side. How do we balance chemical equation? I would like you to stand with this simple, with simulation, because it makes it very, very practical. And if you're able to practice it with this, you won't have problem at all. So we have this. It shows us. This is reactant side, this is product side. Then now we count atoms. Remember, why are we balancing the chemical equation? For every reaction that takes place, it must agree with law of conservation of mass. Whatever amount you start up with, you have to end up with. Each kind of atom has to be equal on the reactant side and the product side. If that doesn't happen, then the mass will not be equal on the reactant side and the product side. So two things. You must make sure that each kind of atom is equal on both sides. If that happens, then the mass will be equal on both sides, reactant side and product side. Here, we are given nitrogen. You see bonded, that's why it's these two substitutes, there are two atoms there. And hydrogen, there's two atoms here. Then NH3, there's one nitrogen and 3 hydrogen atoms, right? Now, when we are balancing chemical equation, there's one thing we must know. We can only change this coefficient. Coefficient, remember, is telling you number of sets of each substance, number of sets, okay? But you cannot change the subscript. You cannot change this. If you change it, then you've messed up. You are not agreeing with the law of conservation. You created, you destroyed the matter. So the first thing you do, I'll advise you always start with the more complex substance. More complex substance. We have, this is elements, and also molecule, this is a compound, right? There's one nitrogen here, there's 2 here. How can we make, this clearly tells us that I don't have equal number of nitrogen atoms. That's 1 on the product side, this is telling me the product side, that's 2 on the reactant side. How do I make them equal? I will add this. You see, now I have 2, right? Now I have 6 of 1, 2, 3, 6 hydrogen atoms. Then how many of these do I add to get 6 here? You see that? So I do this, then I do this. You see that? Now this is balanced. This is balanced. Only the coefficient is changed here. Okay, now this follows the law of conservation of mass. Let's do another one. I want you to pause the video and try this. Type this PhET simulation, balancing chemical equation. I want you to do it. If you start with this, this will be so easy for you. If not, you find it very difficult. Okay, for this one, so hopefully you tried. Let's do it together. So I tell you to always look at the more complex one. You see this one? Oh, everything is equal here, but then oxygen is not. Wow. The left side is telling me there's only 1 and this is 2. So I add this. Now I have 2 on both sides. Now this is 4, this is 2. So what do? I'll add more of this. No, I'm sorry, I added the wrong one. I add this, you see that? Now this follows the law of conservation of mass. There's 2 here, there's 2 here. This makes it very clear. Okay, then we do the other one, this one. So we are looking at this. We start with this. We start with this. Okay. So pause the video and try to get it right. Okay, this is it. Did you get it right? Now, what I want you to do, pause this video and do these 3 games. You see this? You finish this. This is level 1. Okay, you get level 1 correct. You go to level 2. It will take you to level 2. Look at it here. Let me, where is it? You see that? That's level 1, level 2, level 3. You must complete these 3 levels following the example I gave you. If you do not complete these 3 levels, this balance of chemical equation will be more difficult for you. Do this, even if it takes you 2 hours, do it before you come back to the video. Okay? So, in balancing chemical equation, draw, except if you have enough chemistry before, you've done it before and you don't have to do it. But one thing is, many people do this balancing of equation without understanding what they're doing. The drawing makes it very clear, make you to understand the concept clearly. The drawing here, is not the actual structure, the way it should be drawn, but your goal is just to have some representation that will help you to balance it. Okay, now we have 2 atoms of hydrogen, 1 molecule of this, oxygen, 1 molecule of water. So now, how do we balance it? We do the same thing you did in the simulation. There's 1 oxygen here, there's 2 here, there's 1 hydrogen here. So what we do, only 1 atom of oxygen, 2 atoms here. We add another set. Remember, you can only add a set. That means changing the coefficient. You cannot change the subscript. Now, there's 2 oxygen this side, there's 2 oxygen this side. You succeeded in that one. What about hydrogen? Now we have 1, 2, 3, 4 hydrogen. Then we add another set of hydrogen here. So now we have 1, 2, 3, 4, 1, 2, 3, 4. So we have 2 here of this, we have 2. So this is non-balanced. Okay? Sometimes students forget to change the coefficient. There are 2 sets here. There's 2 sets here. This, if it's not written, it means 1. Then for N2H2 NH3, now you have 1 nitrogen here, 2 nitrogen here. So again, we will add.
But I'm also going to be very curious.
We add another set of this.
We think he will be doing on the campaign, which is
okay. And then, so now we have nitrogen. There's 2 here also. 1, 2, 3, 4, 5, 6. There are 6 hydrogen. So we add.
What's the convention for now?
Then we add.
East Palestine, Ohio, is now speaking up.
Okay, now we have 3 here. We have 2 here. So these are balanced equations. Okay. So
When we train.
Let's
you know, explain the cost of chemicals.
look at more examples.
This faster unlike we ever. You know, first.
Okay. This is a more complex example. One thing you must know here, when the in this particular equation, polyatomic ion is there. On the reactant side, there's polyatomic ion, and product there's polyatomic ion. And anytime you have polyatomic ion on the reactant side, on the product side, treat it as one unit. Okay? Like here is PO4, you don't count P separate and O separate, you count it as one unit. So what is happening here is you withdraw, actually this is 2, I don't know why. This is 2, okay? You withdraw your substances, and now this is also polyatomic ion OH, but there's no OH on the reactant product side, so you treat this as individual atoms, okay? So you start with more complex one. There's 3 calcium atoms here. There's 2 phosphates here. Okay, now, do we have 3 calcium here? No. So what we do is we add 2 more of this. So we do this. O, H, O, H. We add another one. O, H, O, H. Okay. Now we have 3 atoms of on product side, 3 atoms of calcium on reactant side. Now, phosphate. There are 2 phosphates here. There's 1 here. So we add another set of this so we can get. Remember, this is not the true structure of these substances. We just want to represent something that will help us to count so that as to balance the equation. This is not the true structures. Okay, now we have phosphate, 2 of them here, 2 of them here. Now, we have to go to count how many oxygen atoms. Remember, this time we won't include oxygen in PO4. We see 1, 2, 3, 4, 5, 6. Okay, so we have to make it equal, so we will add 5 more here. 5 more. We have 1, 2, 3. Okay. One more. Okay. So now 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We balance the oxygen. What about hydrogen? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 2 of these. There are 2 sets. We have 3 of these. There are 3 sets. There's 1. We don't have to put anything here. Then we have 6 of this. Okay. So this is the more complex. Again, you always start with more complex substance. If you have polyatomic ion in your equation, if that polyatomic ion is on the reactant side and the product side, treat it as a unit. Okay, you can't go wrong. So that's the more complicated ones. Remember, you can do this by inventory where you count. Some of you can do it up in abstract, but this is mostly for students who are struggling, students who, remember this is 2, okay? This is 2. Okay. Okay, let's watch
This
the
is an
video.
introduction to balancing chemical equations. We're going to talk about what it means for an equation to be unbalanced or balanced, and then we'll learn the process that you go through to balance a chemical equation. I want to start with a few examples that show the concepts behind balancing equations, so you can really understand what's going on when you work through these kind of problems. We'll begin by looking at this chemical reaction. Hydrogen gas and chlorine gas combine to make hydrochloric acid. So this is how we can express this chemical reaction using words, and we often call this kind of thing a word equation. Now, we can use this word equation to write a chemical equation by taking each one of these things and writing the chemical formula for it, okay? So the chemical equation looks like this. Hydrogen gas, its chemical formula is H2. We have and, the plus. Chlorine gas is Cl2. We get the arrow. And then hydrochloric acid, its chemical formula is HCl. Okay, now if I wanted to be really precise about things, I could put a G in parentheses next to each one of these to show that they're gases, but I'm trying to keep things simple for this video. Now, in order to start talking about equation balancing, which is the topic of this video, we have to look at the atoms in this chemical equation. We have to look at the number and type of atoms that we have on both sides of the arrow. I got some diagrams here so we can do this visually, so we can actually see the atoms and how they recombine during this reaction. Okay, so we got a molecule of hydrogen gas. It looks like this. We got 2 hydrogen atoms, 1, 2. Then we got some chlorine gas. We got a molecule of that. 2 chlorine atoms. Got our arrow, and finally a molecule of hydrochloric acid. So there it is, 1 hydrogen and 1 chlorine. Okay, so now we're going to start talking about balancing equations and balanced equations. First thing that I want to do is figure out whether this equation here is a balanced equation. So here's the definition for balanced equations. A balanced equation has the same number of each type of atom on both sides of the arrow. Okay, so keeping this definition in mind, what I have right here, is this a balanced equation? No, it's not. Here's why. On this side of the arrow, I have 2 hydrogen atoms. Over on this side, I only have 1. Over here, I have 2 chlorines, and over here, I only have 1. So this is not a balanced equation. We don't have the same number of each type of atom on both sides. This isn't a balanced equation, so we call it an unbalanced equation. Unbalanced is just the word for an equation that's not balanced. It has different numbers of 1 or more of the types of atoms on the 2 sides of the arrow. Okay, so this is currently an unbalanced equation. Now, most of the time in chemistry, unbalanced equations aren't particularly useful to us, and we have to make them balanced before we can use them for problem solving or for doing calculations. So often in chemistry, we start out with unbalanced equations, and then we have to figure out how to balance them. So in order to balance this, we're going to make a few adjustments. Here's how we do it. To balance the chemical equation, we change the number of these molecules that we have, and we find a combination that gives us the same number of each type of atom on both sides. Okay, it's a little bit like a puzzle. So it might turn out that to balance this equation, we need 3 of these and 1 of these and 3 of these. Or we might need 2 of these and 2 of these and 1 of these. So we play around with the number of each one of these that we have, finding a combination that gives us the same number of each type of atom on both sides. Okay, so take a look at this equation. Can you figure out what we need to do to 1 or more of these in order to have the same number of each type of atom on both sides? Well, here's what we do. We have 2 hydrogens here, 2 chlorines here, 1 hydrogen, 1 chlorine. So if I get another one of these, okay, if I have 2 of these, we'll then have 2 hydrogens here, 2 hydrogens on this side.
If you're taking anatomy and physiology for the first time, I can guarantee it's not like any course that you've ever taken. And that's why so many students
2 chlorines on this side, 2 chlorines on this side, and now this equation is balanced. Okay, so we've balanced the visual version of it. To balance the written equation, what we'll do is we'll put a 2 in front of the HCl here to show that we have 2 of these, and now the equation is balanced. Okay, so this is the combination. This is the combination of these things and these things that we need to have the same number of each type of atom on both sides. We need 1 of these, and 2 of these to end up with a balanced equation. Here's another chemical reaction. Hydrogen gas and oxygen gas combine to make water. The chemical equation for this looks like this. The chemical formula for hydrogen gas is H2, then oxygen gas is O2, and these combine to make water, which is H2O. Now let's look at how we can represent this visually. Okay, we've got 1 molecule of hydrogen gas, H2. Then we have 1 molecule of oxygen gas, O2. We got our arrow here, and H2O, water, is over here. Okay, so just like we saw previously, on this side of the equation is what we start with. It's our before. We've got our reactants, and over here is our after, our products. Okay, so take a look at this equation and these atoms here, and think about this. Is this equation balanced the way it's written here? And the answer is no. It is unbalanced. Here's why. I've got 2 hydrogens here and 2 hydrogens here. So the hydrogens do balance, but the oxygens don't. I have 2 oxygens here and only 1 over here. So this equation is not balanced as it's written. In order to change this, we're going to adjust 1 or more of the numbers of these different compounds. Okay? Here's how we're going to do it. Take a look. I've got 2 oxygens here and 1 here. So the first thing I want to do is I want to try to balance these oxygens. To get more oxygens on this side, to get 2 oxygens on this side, I'm going to add another one of these H2O. So now I have 2 of them. All right, so I have 2 oxygens here, 2 oxygens here. The oxygens balance. But check this out. By adding this water here, I changed something else. My hydrogens used to balance, but now I have 4 on this side. I only have 2 on this side. But that's okay because I can change the number of these as well. Okay? I used to have 1, so let me add another hydrogen here. Now I have 4. 1, 2, 3, 4 hydrogen atoms over here, and 1, 2, 3, 4 hydrogen atoms over here. Okay, so now this is a representation of how the atoms balance. In order to balance the chemical equation up here, I'm going to put a 2 in front of the H2 because I have 2 of those. And then I'm going to put a 2 in front of the H2O here because I have 2 H2Os. And now the equation is balanced. Here's a really common mistake I got to tell you about. When people are first learning this stuff, a lot of the times they'll say, hey, I have a simpler way to balance this. Here's how you do it. Get rid of this 2 here. Get rid of this 2 here. And then just put a little number 2 right under this O here. Now you have H2 on this side, H2 on this side, O2 on this side, and O2 on this side. It balances perfectly. Yeah, but unfortunately you can't do that. These numbers here, we call them subscripts. You can't change them when you're balancing an equation. They have to stay the same. And here's why. In this equation, we're talking about water. Its formula is H2O, and this is what a water molecule looks like. If you put a 2 here, we're not talking about water anymore. We're not talking about H2O anymore. We're talking about a molecule like this with 2 oxygens and 2 hydrogens. This isn't water. This is now a compound called hydrogen peroxide. So yeah, by adding this 2, you might balance the equation, but it's no longer the equation for hydrogen gas and oxygen gas making water. It's now the equation for hydrogen gas and oxygen gas making hydrogen peroxide. You totally change the meaning of the equation if you mess around with these subscripts. So you can't do that. The subscripts have to remain the same, but you can put numbers in front of 1 or more of the compounds, but the numbers always have to be in front. You can't modify any of these subscripts. When we first start off talking about balancing equations, I love to use visuals like these of the atoms and molecules so you can really see what's going on. But when you're going to be balancing equations on homework or on quizzes, you're not going to be using drawings like this. Instead, you want to be able to balance equations using charts, doing a little bit of math. So I'm going to show you one example here of how you do that, okay? So in this equation, we have nitrogen and hydrogen. Now obviously we have those on both sides. So I've made this little chart, nitrogen and hydrogen on both sides. So the first thing you want to do is you want to write in your chart how many of these atoms you have, right? So we have N2, so that means that we have 2 nitrogens on this side. You can see that from the diagram. H2, we have 2 hydrogen atoms on this side, and then we have the arrow. And then over here, we have N, so we have 1 nitrogen atom, and then we have 3 hydrogen atoms. So to start balancing this, you want to look at where you have an imbalance of atoms, where you don't have the same number of atoms, and you want to think about what you could multiply one of these compounds by. Okay, so let's look at nitrogen right here. We have 2 nitrogens here, we only have 1 here. Okay, so one thing that we could do to start out balancing this is we could put a 2 in front of NH3 here. So that would multiply this whole thing by 2. So now we'd have 2 of these, and that would give us 2 nitrogens. And now we have 2 times 3, which is going to give us 6 hydrogens. Okay, so that's how we use this chart. Now that kind of changed these numbers, so let's look at what's going on over here. Okay, so now the nitrogens balance, but now the hydrogens don't balance. I have 6 here, and I have 2 here. Okay, so what could I multiply something by here to fix the hydrogens? Well, I have 2 right now. I want 6, so I could put a 3 in front of this. It would look like this in our visual. Now we have 2 more hydrogens, and that gives us 3 times 2, 6 hydrogens here. So we can keep track of these adjustments that we make using charts like this that show us how many of each atom we have on both sides. We multiply something by a number in front of it, and then we change the number of atoms. So the best way to get good at this is to just do a whole bunch of practice.
Okay. Here are the practice questions. Show all your work. You can use inventory, counting, like you saw in the video, counting each kind of atom on the reactant side and each kind on the product side. You can use drawing, whichever one. You are free to use any one as long as you show your work. So pause the video and balance the equation. If you add coefficient without writing anything, that's not good. I encourage you to show your work. Hopefully, you got this right. This is the answer. And then we have challenging questions on this. Very important. You get this challenging question right, it means you understood everything. If you didn't get it right, that means you need to go back and watch the video till you get it right, because I do not have any answer for these 2 questions. I thank you for watching.